You are well acquainted with these measuring instruments. The panel meter and the ammeter section of the PSM-6 are used to measure current. The voltmeter section of the PSM-6 measures voltage, and the ohmmeter section measures resistance. These meters are intended for day-to-day use in common electronic circuits. They serve this purpose very well, but they are not precision instruments. In most circuits, the components have a wide tolerance, so there's no need of measuring exact values of current, voltage, and resistance. For instance, when we are measuring this 15,000 ohm resistor, we'll be satisfied with any reading between 12,000 and 18,000 ohms. This one measures 14,000, and that is very good. But there are many situations where precision measurements are necessary. At times, it is necessary to measure values of voltage, current, resistance, power, inductance, capacitance, and frequency to an accuracy of 0.1%. Such precision instruments normally make use of a special circuit which we call a bridge circuit. In this lesson, you will learn the relationship of current, voltage, and resistance in such a bridge circuit, as well as some of its applications. Let's see how a bridge circuit is constructed. For the sake of clarity, we will start with this simple series circuit and gradually build it up until it becomes a resistive bridge circuit. Here we have a 20 ohm resistor in series with a 25 ohm resistor. This dropping resistor reduces the voltage. It is not part of our bridge circuit. You already know that a series circuit is a voltage divider. The voltage is distributed according to the ohmic value of the resistors. Now I'm going to take a similar series circuit and connect it in parallel with this one. Now we have two series circuits in parallel with each other. Each circuit is a parallel branch. Let's measure the voltages. I'll set the meter to DC volts, the range switch to 10, and we will read the 0 to 10 DC scale. Here we have 2.2 volts across the 20 ohm resistor and 3 volts across the 25 ohm resistor. In branch 2, we have a 15 ohm fixed resistor and a variable resistor which is set to about 19 ohms. We have the same voltage across both branches, and this voltage divides between these resistors. Then we must have 2.2 volts across the 15 ohm resistor and 3 volts across the 19 ohm resistor. Let's measure these voltages and be sure. Here we have 2.2 volts. And here we have 3 volts. So Ohm's law is still proving correct. Since we have 2.2 volts across resistor A and 2.2 volts across resistor C, points 1 and 2 must be at the same potential. Let's verify that with the voltmeter. We measure from point 1 to point 2, and we get a 0 indication. Since we have no difference in potential, we should be able to place a conductor between points 1 and 2 and have no current through the conductor. I'll use this galvanometer to determine if that is true. This galvanometer makes a very sensitive detector. Any difference in potential between points 1 and 2 will cause current through the meter. There is just a little current. I'll adjust this rheostat and bring it back to 0. This circuit is now a resistive bridge. And since points 1 and 2 are at the same potential, we have a balanced condition. Voltage A is the same as voltage C, and voltage B is the same as voltage D. In this condition, we call this a balanced bridge. Notice that the bridge is composed of 2 branches, and a detector circuit divides the branches into 2 legs each. Legs A and B form branch 1. Legs C and D form branch 2. If we change the resistance of any of these resistors, we will unbalance the bridge and upset the ratios. Watch the meter as I vary the rheostat. As D increases, point 1 becomes positive with respect to point 2, and current flows through the meter from right to left. By decreasing D, we can bring the circuit back to balance and unbalance it in the opposite direction. Now, point 2 is more positive than point 1, and current flows from left to right. Notice that with a single control, we can cause current through the meter in either direction, and we can vary the quantity of current. This feature of the bridge circuit makes it extremely valuable in many applications. One main purpose of such a circuit is to measure precise values of resistance. With a resistive bridge circuit, we can measure resistance values that are accurate to 1/10 of 1%. Let's examine the circuit again to see how this is possible. Voltage A is exactly the same as voltage C. We proved that in 2 ways. We measured the voltages, and we have no current through the meter. This action also proves that voltage B is exactly the same as voltage D. This means that we have an exact ratio between voltages A, B, C, and D. This ratio is A over B equals C over D. It is not necessary that we know these voltages. If there is 0 current through the detector, this ratio is always true. What does this have to do with resistance? We have a direct relationship between the resistance and the voltage. The voltage which appears across a resistor is directly proportional to the resistance. This means that in a balanced bridge, we have exactly the same ratio for the resistance as we have for the voltage. With this ratio, when we know the value of any 3 resistors, it is a simple matter to calculate the value of the 4th resistor. Don't allow yourself to become confused when you see these resistors numbered other than with our A, B, C, D designations. Regardless of what the resistors are called, our ratios of A, B, C, D will hold true. Just remember these positions. The resistance in this position divided by this one is equal to this value divided by this value. When measuring a resistor, we may insert the unknown resistor in any position. In most cases, it is placed in the branch with the variable resistor. The variable resistor is then adjusted until we have 0 current through the meter. Now our ratios are correct. The variable resistor generally has a calibrated dial, so we will know the value of 3 resistors. We simply substitute these values into the equation and solve for the unknown quantity. Now let's remove this galvanometer and use a motor as a detector. On this trainer, we have replaced the galvanometer with this motor. Suppose that this motor is a motor used to correct the trajectory of a missile. When the missile is on course, the bridge is balanced and the motor does not turn. Any deviation from the proper course will unbalance the bridge and cause the motor to turn. Off course in one direction causes the motor to turn clockwise to correct the course. Off in the opposite direction causes the motor to turn counterclockwise to correct the course. Slightly off balance causes the motor to turn slow. A greater off balance causes the motor to turn faster. Bridge circuits will be encountered in space vehicles. In automatic pilots, in antenna positioning circuits, in ground control approach radar, and in any other system which requires a highly sensitive control circuit. The resistive bridges that we have been discussing are commonly called Wheatstone bridges. The next time you see a Wheatstone bridge, it will probably look like this. The circuit is exactly the same as those we used previously. We have simply eliminated sections, which gives the schematic a more compact appearance. Remember that the ratio is determined by the position of the resistors. In this case, we have R1 over R2 is equal to R3 over R4. This is the same as the previous ratio using the letters A, B, C, D. Here are some very important points that you must remember about the bridge circuit. It is widely used for both precision measurements and control devices. When balanced, points 1 and 2 are at the same potential, and the detector has zero current. Also, in a balanced condition, A over B is equal to C over D. And this ratio is true for both voltage and resistance. When out of balance, one variable resistor can control both the direction of current and the quantity of current through the detector. So far, you have studied series circuits and parallel circuits. In your next lesson, you will study series parallel circuits. This will be a combination of series and parallel arrangements in the same circuit. A review of both series and parallel circuits is highly recommended before your next lesson.